All right, hope you guys all had a good spring break. Just to remind you, we're going to have a midterm exam this Friday. During lecture, it's going to cover Unit 5 on classification, Unit 6 optimization, Unit 7 neural networks. There will not be any tree or ensemble material on it. I've already posted the equation sheet and some practice midterms. Any questions on the upcoming exam? Okay, great. So let's get started with this new model where we're going to learn about large language models, which are kind of driving the artificial intelligence boom we're seeing now, and then transformers are the main network architecture that's used for those models. So we'll learn about those things. So what we're talking about in this unit is an example of generative machine learning, which is a task that we haven't talked about yet in this course. We focused on supervised learning, where you have examples of feature label, and then you train with those examples, and at test time, you get a feature vector, and you're asked to produce a label. So in generative machine learning, this is an unsupervised task, which means that there are no targets. There's just a data set of, you could say, features or examples, and your objective is to generate randomly a new X that looks a lot like these X. So you could imagine this with images. Maybe you're given a large database of cat images, and you're asked to create a new cat that looks very cat-like, but is not just a copy of one of the cats you've trained on. So in this case, we're talking about text, and so the idea would be like, we have lots of text for training, and we want to generate new text which looks a lot like our training text. And there's different ways to do all this kind of generative stuff. So we're going to focus on what's called autoregressive text generation in this unit. In autoregression, you first train a model to iteratively predict the next word from a block of preceding words. I guess I should cross out the word iteratively here. It's not really important at this stage. So you train a model to predict the next word from a block of words. Now, even though the overall task is unsupervised, we can formulate this training as supervised because if you give me like a long string of text, I can chop it up into small blocks where I know the preceding words as well as the next word. Okay, so I can create a target/label data set from that, and then now I can do supervised learning as my training. Does that make sense? Supervised means you have targets and labels. The high-level task has no targets. Okay, so once you've trained a model to take in a block of text and predict the next word, let's say, now for generation, you can use this iteratively, where you seed it with an initial block of text, and then you predict the next word. And now you move your window forward where you say, okay, now my block of text is all but the oldest word of what I was given. I concatenate the new word on the end. And now with this, I can predict the next word. And you just keep predicting the next word on to your sequence and moving along. So that's the idea behind this autoregressive generation. Is that idea pretty clear? Okay. So state-of-the-art large language models, they work on words or parts of words, but that ends up being too computationally intense to do on our laptops. But what we can do is we can do character by character generation. So again, you're given a string of text, and you just predict one character at a time. And this is, you can make these small enough that you can train them on your laptop in not that long. And so what we're going to do is we're going to use a data set of Shakespeare text, and we are going to try to generate new Shakespeare-like text from that. And we'll do this, we'll build everything from scratch, so you can see exactly how these things are constructed. And we're going to use all the same components as you see in today's large language models, but just sort of scaled down to sizes that we can run on our laptops. Okay, any questions? Okay. So we're going to use this tiny Shakespeare data set. This has 40,000 lines from Shakespeare's plays and poems, which totals about 1.1 million characters. So here is kind of just printing out the first 1,000 characters. This is just one big long text string. So you can see that it's like in a play. So this is the speaker, first citizen, and this is what they say. And then there's a new line, and then another speaker, what they say, and so on. So this is pretty similar to the format all through. It has kind of like speaker, colon, and then text. And if you look through here, you find that there's there's a few words that are would be a bit strange in today's text, and maybe spellings that are strange. So, when you see what's generated, just keep that in mind. Things might sound a little weird to us, but the input text is a little weird too. Okay, if you wanted to train, even better with more data, you can actually find his full works, which are 181,000 lines. You can actually download that if you want to play with it. Okay, so the first thing we have to do in the code is we have to figure out what are all the characters that we're going to work with. What's the vocabulary for our data set? So you can do this with some Python commands, and you find that there are 65 unique characters in these 1.1 million, and here they are. If you go through, you'll find all the capital letters A through Z, all the lowercase letters A through Z. You only find one number, which is 3, and you find several punctuation marks, including a space and a new line. Okay, so that's what we're going to work with. And now these are characters, and as we know, when we do machine learning, we need to work with numbers. So we just need to transform these characters into numbers, and we're going to do that in a very straightforward way. We're just going to assign a unique integer to each of these characters. So actually the new line, which is, you can't see it exactly, but that's what causes this character turn, that is going to be character number 0, and then the space is character number 1, and then the exclamation mark is 2, and so on, all the way to this lowercase z, which would be 64. Okay, so basically we make this encoder using this lambda function, which is just going to take in a string of letters that are, they have to be in the vocabulary. It's going to take those in, and it's going to produce a Python list of integers. So this is not a NumPy array, it's a Python list, so we'll have to keep that in mind in some of the code. Sometimes we need to go from NumPy arrays to lists and back. That's what the encoder does. And then the decoder takes in a Python integer list with numbers between 0 and 64, and then it gives you back the string that corresponds to our encoding model. Okay, so this is what we're going to do. There's other options. For example, if you try to encode something with numbers other than 3, you'd find that you get an error. And if you wanted to handle those, if you wanted to handle all kind of common things, you could use this UTF-8 text standard, which contains, because it's based on 8 bits or a byte, it contains 256 characters. So all the usual ones, all the usual numbers, punctuation, plus a few kind of strange ones. It still doesn't handle, all foreign characters and so on. There's other ways to encode those, but you would then get a larger vocabulary size. So because we're just working with this data, and we want to save space and all that, we're just going to use the smallest possible vocabulary that we can, but you can see how other things are also possible too. Okay, great. Any questions? Yes?
So that vocabulary, the unique characters, we just chose that from our data set?
Yeah, we went through everything in the data set, and we found that they only use those 65 characters. So if we want to generate new data like our data in the data set, it should be enough to use those 65 characters.
Okay.
Like we would never generate a 1 or a 3, because that was never in the Shakespeare training data.
I see. Okay.
Yeah. Yes.
Is that where all the computational intensity comes from, the vocabulary?
Oh no, I mean you'll see there's many ways in which you can scale up models to get complexity, but at the end of the day, you can imagine that if you make your vocabulary bigger, then a lot of other things will need to get bigger too. So there's just like one of the many ways that, yes, things can grow as your vocabulary grows. Okay, great. Any other questions? Okay. All right, and then we also need to split our data, those 40 or 1.1 million characters, into training and test. And this is an example of what you could call time series forecasting, which is an application that we haven't really talked about yet in this class. And time series forecasting is just sort of a more general class of problems where you try to use the past to predict the future. So you're given some time series of, it could be like scalars, or it could be a time series of vectors. We briefly talked about like stock market prediction on the first day of class. So that would be like an example. You could collect various features about a certain stock price and then use those to try to guess what the price is going to be tomorrow. So in this class of problems, you can't do train test splits using shuffling, which is what we've done for most of our data. So here's sort of a visualization. So imagine that we just have now scalar data. So this is like all these 1.1 million Shakespeare characters, and we've converted them to integers. So now we have like 1.1 million integers. So if you think about a sample that we're going to give to our model, it's going to have kind of a small block of past time points, and then we're going to try to predict, and these would be like integers, integer representations of our characters, and we're going to try to predict one character in the future. Right, so for our model, this is what it's going to see. This is what a sample is going to look like. And here, we're choosing the sample starting at a certain time. And so here's maybe another sample and another sample. So now you can see that if we shuffle these samples randomly into training and test, you could get a situation where this was your training and this was your test. And you can see now that a lot of the features are going to be used for both training and test, right? And that's kind of dangerous. It's kind of like you don't want any overlap between training and test. So this kind of shuffling-based split is not going to work for us. So what we're going to do is we're going to take this long sequence and we're just going to split it somewhere. like here, and we're going to say, okay, all this will be your training data, all this will be your test data, and you can see there's absolutely no contamination from training into test. Okay, so anytime you're doing some kind of time series machine learning, you have to do something like this. You can't use random shuffling. Okay. Okay. Any questions? All right. And by the way, the stuff we're talking about in this unit, even though it's based on text, that's kind of our main application, a lot of the ideas can work with any data. So if you're doing, for your research, you're doing some sort of time series forecasting and it's not text-based, like still 90% of the concepts here can be used. Okay, so we're going to start with, just to kind of, since we're starting from scratch, from knowing nothing about this, we're going to start with the simplest possible model that we can really imagine, which is called the bigram. And the bigram uses only I don't remember, did I mention the word token yet? I might have. Okay, I forgot to say this. Once you take your characters and you convert those characters into integers, you call the integers tokens. And when you're dealing with larger, like word level large language models, you might take words or pieces of words and assign an integer to those, and those are still called tokens. So if we start talking about tokens, then our conversation could be applied character-wise or word-wise. It's more general. So often I'll just refer to these integer numbers as the things we're trying to predict as the tokens. Okay, so in the bigram, you use only the most recent token, which is going to be an integer. We're going to, for the purpose of these notes, we'll call this an integer between 1 and capital N, where N is our vocabulary size, 65 in our case. So we're going to use just the most recent token to predict the next token. And we're going to use K as the token variable. And I is the time variable. Okay, so I is the time index. That's always going to be 0 or higher. N is vocabulary size. And so, so for example, the bigram would be trained so that it sees B and tries to predict E. And then it sees E and tries to predict F. And then it sees F and tries to predict O, and so on and so on. So it only uses one character to predict the next character. So it's very simplistic in that way. We don't expect it to work well, but it's a place to start. And the particular way that it does the prediction is also pretty straightforward. It's all based on this conditional probability mass function. It's the probability of the next token given the current token. And so just from our basic probability, this conditional probability, we can also write this, this is like k plus 1 given k. You can write this as probability of k and ki and ki plus 1 divided by probability k. And now we can, these are based on random variables that we don't know, but we have data. We have empirical data, so we can basically just come up with the empirical approximations of these. So for example, to find the numerator, for every possibility L, all possible tokens, we just count how many times have we seen that token in our data set. So this is an indicator function that turns into 1 whenever this is true, whenever the ith token is L, and otherwise it's 0. And then we just sum this up over all n, and if you wanted to turn that into an empirical probability, you could divide by n. Okay, so if you have the 1 over n's, maybe I'll just throw them in there. They don't need to be in there because they cancel, but they could be in there. So now this is the empirical approximation of this. And then this is the empirical approximation of this. So here what we do is we go through all the consecutive pairs in our data set, the first and second, second and third, third and fourth, and we count how many times does that pair equal this pair L and K. And we fill up a matrix for all L and Ks. So we just go through with a big for loop over our data set, and every time, so actually how we do it is we look at the current token, we know that that's going to be L, and then we add the value 1 to the kth. So if our next token is K, then we add the value of 1 to the kth column and lth row of a matrix. So we just keep going through character by character, and we just keep adding counts to this counting matrix. And when we're all done, we get a matrix because this is basically needs to be a conditional PMF, we need that for the lth row, this thing needs to sum to 1 to be a PMF. So we just normalize all the rows so that they sum to 1. Okay, so that's what we do. We just go through, count all the times we see pairs into this P matrix, we normalize so the rows sum to 1, and now that's an empirical approximation of this set of PMFs, where every row is a different conditioning option. So we have an n by n matrix whose lth row is a PMF of the next token given that the current token equals L. Does that make sense? Okay, so it's very easy to code. Now if we wanted to make a hard decision and our current token is L, then we would look through the lth row of this matrix and we would find the maximum probability, which is the most probable next token value, and we would just set that as our best guess of the next token. Okay, so that's the bigram. Any questions on this? Okay, so when we generate text, though, we're not going to choose the most probable next token, because if you did that, then like for any given character, there would only be one next character you would always choose, right? If you always choose the most likely one. So you just get in this loop of predicting the same sequence over and over. So instead of that, what you actually do is you have this PMF. So let's say you initialize token K0. So in the code, it's just set to something of our choosing, like the letter A, capital A, for example. Now, we know for capital A that corresponds to one row in our matrix, and now that row actually gives us a PMF over the next token. So rather than choosing the most likely next token or next character, we're going to sample from that PMF. So usually we'll be taking, with the highest probability, we will be taking the largest value in the PMF, but once in a while we will sample less likely ones. And if all the PMFs are positive, then we will eventually sample all of them if you wait long enough. Okay, so that's how we start with token K0, and we have a for loop, and then token K1 is a random draw from that PMF, and now we go through again, now conditioned on what we just generated, we draw another random one for the next one, and now we do another loop, so now conditioned on that one we just drew, we draw another one, and so on and so on. Is that making sense? So that's this auto-regressive, because it kind of feeds back on itself. That's auto-regressive text generation. You keep drawing random things, and then based on those, you draw new random things, and you just keep going as long as you want. Okay, so questions on that? It's very important, so I want to make sure that this part is understood. Everybody's understanding this idea? Feel free to ask questions if you're not. Yeah.
Could you really kind of just can you write an example or
Sure.
Visually how that's?
Sure. So, maybe we have 3 tokens. Let's just say A, B, C. And so we can make a matrix where every row is a PMF, so it's non-negative numbers that sum to 1. So maybe this is like 0.8, 0.1, 0.1. And then maybe here we have, I don't know, like 0.5, 0.2, 0.3. And then we have like 0.3, 0.4, 0.3. Okay, so let's say I initialize with the letter A. Now, I look at, I'm at this row because this is the previous, and then this is next. So if the previous letter was A, then these are the probabilities that I would sample A, B, or C. So with 80% chance, I will pick a B, and with 10% chance, I'll pick an A, and with 10% chance, I'll pick a C. Okay, so I start with an A, and I do a random, and so 4 out of 5 times, I'm gonna get a B. So let's just assume that on this time, I got a B. Okay, now I need to generate the next character. So I say, okay, my current character is a B. So I go to this row, and I say, okay, I'm gonna draw a new sample. So 50% of the time, it's gonna be this, 20% this, 30% this. So this time, maybe I get a C. So now I put a C there. And now C, for the next time, I look and I see, okay, if C is my current character, then this is my next character. And so maybe I pick C again. I draw C again. And so I just keep repeating this as long as you want. And I generate a string of characters. Is that making sense? Okay, good. So that's the bigram. Let's think of even some simpler things, because as you'll see, the bigram doesn't work well. So you might even wonder, like, is this even working? And it is working, it's just very limited. So let's think of, like, what's the simplest possible thing you could do? Well, it's probably just to pick letters at random, right? And not by random, I mean completely random. So you have 65 possible characters, so with probability 1 over 65, you just uniformly choose. That's this option, just sequence generation using the uniform PMF. So this is not even autoregressive, because it's just literally, you're not even using the past. At every time, you're just saying, I'm going to draw a character at random. I'm going to draw another character at random, and it's uniformly random. So this is another option. This is like probably the simplest thing you can do. And you might say, well, that's kind of silly, because I know that some of these characters are not really going to show up often, like maybe the punctuation marks. So, and maybe the vowels will show up the most often. Like if you play, like Scrabble or something, you know that certain letters come up more often. So you might say, well, if I'm not going to look at the past, fine, but I should at least respect the prior probabilities that every letter shows up. So you can measure those. You can just go through your data set and kind of make a histogram or a count of how often every character appears. And then that gives you this prior PMF. And now you can sample from that. So if the letter A is the most common, then you'll sample from that most often. Okay. All right. So these are like, this is the autoregressive approach, and these are just some simpler baselines for comparison. Okay, any questions? Okay, so let's see what happens. So we can compute the test accuracy because, we have this training data we trained on, and we have test data we can test on. So, and this is what we get. So if you use the uniform PMF, we end up getting a test error of 0.04. If we look at the empirical prior PMF, it's better. It's like 15% accurate. And the bigram is like 27%. Okay, so here's some examples. So if you generate uniformly, you see it's just complete garbage. You get a lot of punctuation. Very rarely do you get a character return. Empirical prior, you can see that things you're drawing these like vowels much more regularly. What you get looks, I would say, a lot better than this, but still it's pretty bad. And then from the bigram, you get things that have, it's still like not really words, but at least you notice that there's sort of common patterns like vowel and then consonant and then a couple vowels and a consonant, this kind of thing that you see in English. So these are closer to words than these are. Okay, so that's the bigram and some of the baselines. All right, any questions? Yeah.
So when you initialize, like, how do you know what to set your K not to? Because we, like,
Oh, I just chose it.
Okay. But like in an actual thing?
So probably you would do this. You would you figure out this empirical PMF, and then you would just draw the first one according to that. But just to keep the code simple, I just said, the user can choose this, and then you can see they all start with the capital A. Okay, all right. Okay, so you might then say, okay, well, we learned about some other classification methods earlier in the course, like multinomial logistic regression. So if what I'm doing is I'm predicting the next character from the previous character, which is this kind of the setting of the bigram, can I just apply multinomial logistic regression, and what would that look like? So one important thing now is that our feature is going to be categorical, right? Because it's a token, it's a character, it's not an ordinal thing. So we just have like capital N different categories for our feature. So we learned that the way to handle that is through one-hot coding. So in these notes, I'm going to use this boldface delta, kind of like the Kronecker delta from sigma processing. I'm going to use that as the notation for a one-hot vector. And so like this guy would have zeros, and then there would be a 1, and this would happen in the position, it's like the k-ith position. Okay, because here I'm saying that that's where the non-zero occurs. Okay, so we could use this one-hot coding. So if my current character has the value, so if L is the location I'm looking at in this vector, I would find a 1 when L is the current character token, and otherwise I find zeros everywhere else. Okay, so that's how I would want to set up my feature vector. And then we also know that with MLR, this is exactly how we wrote it before. Now, okay, this thing would be my capital X, which is going to be that one-hot vector. And I think this is very familiar to you guys. So the way you do MLR when there's, MLR is where there's more than 2 classes. So here there's capital N different classes. And so you create these one versus rest binary classifiers. And so for the, this is K is kind of like you're saying this is the score if it's class K versus the rest. And you create that score with a scalar bias and an inner product between a weight vector and your feature vector. So this is exactly what we saw back in Unit 5, which you'll be tested on this Friday. So this is exactly what we did. And then this is the softmax. So you just plug these scores, you exponentiate them here, and then you have this normalization so that this overall thing is a PMF. And now, usually we would write this as Y for our label, but in our notation now, we're calling it KI plus 1 because that's the next token. And this is just kind of like the hypothesis that it's K would be this. And then for all the different little k's, we would have another version of this. So at the end of the day, you have capital N different biases, capital N different weight vectors of length n, and that's your MLR model. So is this part kind of familiar, the MLR part? Okay, so if you look closely at this model, though, you'll notice that there's a redundancy. It's kind of reminiscent of what we found when we first applied one-hot coding way back in Unit 2 regression, is that we noticed that, like there's too many parameters. So here, this is essentially what we called one-hot coding, the intercept. So here we have n different possible intercept weights for our n classes, but then we have our original intercept weight. So we actually have like n plus 1 parameters to represent n possible intercepts. So there's a redundancy of 1. And there's different ways to handle this. Back in Unit 2, we said, well, you can kind of make this vector 1 shorter, but another thing you can do is you can just set this guy to 0. Take that original one out of the equation. And that's a little bit clearer for what we're doing now. So we're just going to do that. For all the different k's, we're going to set little bk equals 0. And then we just have a simpler model. And we can write that, the resulting model we can write like this. And these are just, these so this is like the lth element of WK. Okay, so here we're using, we wrote it in terms of the score vector z, and now we're plugging in this equation, which relates things back to the previous token. And if you write it for a previous token being L, then you end up using the lth weight of the WK vector. And this is exactly what you get for MLR. Is that looking familiar? Okay. So at the end of the day, to train this, you have this weight matrix, capital W, which is an n by n matrix, and you just minimize the cross entropy on your training data set, like we know about. And so you get this W coefficient factor. But if you kind of take a step back, you notice that, well, actually, this is just another way to describe this conditional PMF that we saw with the bigram. Right? So here, these are what you would call like the logits of that PMF, because these WKs are like the real numbers that you exponentiate, or the real numbers that you put through a softmax to get the PMF. So, so you can think of them as coefficients, but you can also think of them as logits. They're just real numbers. Okay, so the final message is that the bigram is just multinomial logistic regression. However, rather than doing an empirical way of computing those conditional PMFs by counting them up, you're actually representing them as a learnable matrix, and then you're using cross entropy. You're running a stochastic gradient descent on your training data to tweak all these parameters until it minimizes your cross entropy. So, but in Spirit, you're once again learning these PMFs just through a different way. Does that kind of make sense? So both methods, bigram and MLR, are based on learning some approximation to these empirical PMFs. This is the PMF of the next token given the current token. Bigram does it by counting things up empirically, and MLR does it by representing this as a weight matrix and then training to minimize negative log likelihood or cross entropy. Okay, so you might then wonder, well, okay, different ways of training, do they lead to the same place? And actually they do. So this is, I just picked one of the tokens. This is actually the 0th token. For the current token is 0. This is the index of the next token. And I'm plotting the PMFs superimposed of MLR versus our empirical bigram. And you can see they line up almost perfectly. There's like a few places that maybe, okay, here, like maybe one of them is here and one of them is here, so it's not perfect. But, and here it's not perfect, but otherwise it's, very close. And probably if I would have trained MLR longer, because I think I only trained it for one epoch, it probably would have gotten even closer. Probably the more you train it, the closer it gets. One can probably prove that it will eventually converge to the empirical PMF. So it's just a matter of how long you train it. Okay. All right, so basically MLR is just another way to think of the bigram. One slight difference is that when you count things up, you can get exact zeros in your PMF matrix. Like, you may find that there was never in all the data, a transition from one character to another. So you would get exactly 0. And so that means, like, if you generated based on that, you would never, ever reproduce that. Whereas with MLR, since your weights cannot grow all the way to negative infinity, these will always be positive. And so there's always a chance that you can generate. Maybe the chance is tiny, but you can always generate anything. So it's just a small thing. If you plot, so here you can see it looks like zeros, but if you plot them on a log scale, then you can see that the MLR ones are finite or they're positive, and then the bigram ones are exactly 0. Okay, so that's the bigram. Any questions on bigram or MLR? The MLR connection is important because, as we know, that's actually how we train things right? We don't usually do like empirical fitting of PMFs. We usually parameterize things, and then we train them to minimize some loss. So that's an important kind of connection. Okay, so can we make this better? Can we scale it up? So conceptually, the most simple thing to imagine to do is just to look at a larger window. Rather than only consider the current, let's consider a total of T tokens. So here we have a block length of little t. Okay, so that, yes, conceptually you can definitely, this makes a lot of sense. And in fact, like, if you could really do this, this is probably actually the optimal way to do it. Because this PMF kind of tells you everything. The trouble is implementing this. So if you think about how many possibilities are there for this combination of T different tokens, right? So here there's n possibilities. When I add the next one, I have n squared. Right? Together, these two are n squared possibilities. And then I add another one, I go to n cubed, and so on. So basically, if I'm looking at a block length of t, there's n to the power t possibilities of the most recent tokens. And for each of those possibilities, I have to learn a PMF. So that itself has n values for every one of those. So in total, the number of parameters we would need to learn is n to the power t plus 1. And so for our current vocabulary size of 65, if you look at different values of our block length, you can see how many parameters we would try to learn in our model. So with what we did with the bigram, our n by n matrix had, this is n squared, so there's 4,000 parameters. Okay, not a problem. If you have a block length of 274,000 parameters, still not a problem with, probably even a laptop. I think you could do that without a problem. But then 3 is 17 million. Okay, that's, bigger issue. Then 4, it's like 1.2 billion. Okay, so now probably your laptop can't do that, or it can't do that while keeping everything in memory. And then you go to 5. This is only 5 characters, right? That's nothing. 75 billion, 6, 4.9 trillion. So it just gets out of hand really quickly. And still, if you think about generating Shakespeare text character by character, you probably need a window much longer than 6 characters to get reasonable outputs. So basically, like, yeah, the idea theoretically sounds good, but in practice, it's just, there's no way you can do this. Okay, so we're going to have to think of some other approaches. All right, so any questions about the n-gram? Okay, so so what we're gonna do is we're gonna try to get out of the sort of integer world, because if you think about what we're doing here, we have sort of constrained ourselves to working with kind of integer level data. So we have like integer possibilities here, we have integers here. Let's think more about like real numbers and building real valued feature vectors. And because that's how we've always built our classifiers and our regressors, with actually like real numbers. And in fact, we kind of did that over here with the logistic regression. What we did is we used one-hot coding to take our integer token and convert that into a real number vector of length n, right? So that's how we did it. And yes, you could say that's basically the method that the bigram uses, is it converts every integer into a vector that's orthogonal to all the other vectors, right? Because if you think about these, so I have like theta 0, theta 1, theta 2. Let's say if my vocabulary size was 3, then these would be the 3 different vectors that I would use as feature vectors. They're all orthogonal, normal vectors. And so you could say that I'm taking my token and I'm representing it in the, R3, the real number, 3-dimensional space, as one of those 3 vectors. Okay, so that's the point I'm making here, is that bigram implicitly represents each token using one-hot coding. And so if you think about it, is that the right thing to do? So we talked about this back earlier in the course. We said, well, if you have these categories that are really completely unrelated to each other, you don't want to impose anything onto your understanding of them, then they should actually be orthogonal. That's the right thing to do. But now when we think about characters or words or whatever we're using in this case, it doesn't actually work that way. So as we know, like all the vowels kind of share some commonalities, right? They're not all like, at least when you compare them to consonants, they're kind of more similar. And then the punctuation, they kind of work in a certain way that's different from vowels and consonants. And then capital letters behave different than lowercase letters and so on. So it's like you don't really have 65 orthogonal dimensions that are completely unrelated to each other. The reality is not, it doesn't work that way necessarily. Maybe what we can do is we can actually, to save computation, maybe we can squeeze them into a lower dimensional space. So maybe like I put all my different tokens, I code them all as vectors, maybe just in 3 dimensions. And I squeeze them in there, but maybe in a way that works well for predicting the next token. So that's the idea behind embeddings, is you represent each token as some learnable vector, we'll call it E sub k for now, in a space of dimension d, which is something we can choose. We can work with, we can try d equals 3, d equals 4, whatever. We can try different d, but the main idea is to represent each token as a vector in some d-dimensional real space. And that's called an embedding. And then typically what you do is you store these embeddings in a matrix. So now this matrix we're talking about, we'll call it capital E, has dimensions d, which is the parameter for the dimensionality of the space, times n, which is how many tokens I have to represent my vocabulary size. Sometimes you call E the codebook. And remember, just from the linear algebra perspective, if you want to extract the token, let's say you just you stack all your tokens into this matrix you stack your embeddings into this matrix. So the first column is the embedding for token 0, the next one for token 1. If you want to extract one, you can just take that one hot coded vector and multiply that by E, right? And what that does is you have this matrix of columns, and then you have a 1 there, and when you multiply it, this 1 will extract that column. So this is just extracting the kth column of your E matrix is done by just multiplying E on the right by delta K. Okay. All right, so this is the embedding idea, the embedding matrix. And now there's different ways that you can learn this matrix. So there's like standalone methods that are not based on next character prediction. They look at language in a certain way, or they look at, usually they do this with words, not with characters, but they'll use some kind of language-based ideas to say this is a sensible embedding, and they use algorithms to create this E matrix. And so one of them is known as GloVe, pretty successful one, and there's a demo which plays with GloVe in the unit. But the way that it's usually done and the way we'll do it is you just treat E as another learnable parameter in your model. So this first stage of processing is going from tokens to these embeddings, and then everything after that works on the embeddings, and you just have E as a learnable matrix. And you minimize cross entropy or whatever at the end, and E is just one of the many things you learn. Okay, so there's a lot more to say about embeddings, and we'll talk more about them later, but for now, it's just a way of converting these integer tokens to real vectors so that we can process them with all the methods that we learned about so far. Okay, any questions about these embeddings? Okay, so we saw at the n-gram, it was not possible to grow the block size beyond just like 2 or 3. But now what we can do is we can just stack our embeddings into a big vector, and it's not that big, right? So each one of these in our case is like 65 dimensional. So if I want to use 10 of them, then I have a 650 dimensional vector, which is less than I think we saw with MNIST and other examples. And 10 is already impossible with the n-gram. So I can create a feature vector like this, stacking my embeddings, and this is just showing how I would handle it with linear classification. So similar to MLR, you have a bias for the K versus rest classifier. You have a weight vector, which now is whatever dimension this is. And then you train, and this is your score. You don't need the softmax model to make the prediction, but you do need the softmax model to train these. And we're also saying, okay, but these embeddings are also learnable. So, okay, this is not a very convenient way to write everything because this is mixing the learnable E stuff with the input data K stuff. So let's write it a slightly different way using this idea. So what we can do, we can replace this vector with a matrix where we have these shifted versions of E, like this, and then this will multiply this to extract this. This thing will multiply this to extract this, and so on. So now this is all the learnable stuff, and this is just the input data. Does that make sense? So now when you step back and say, okay, what do I actually need to learn in this model? I need to learn my biases, my weight vectors, and my embedding matrix. So the embedding matrix we know is size d by n. If you think about these, so if I'm using t, block size of t, and each one of them is n, so this is a total nt length. This is d-dimensional, and there's t of them. So this weight matrix would be every column is TD dimensional, and then there's n different columns because this is like a K versus rest. Okay, so this is just showing if you stack the embeddings this way into a block of embeddings, this is how you would do a linear classifier. You could also imagine doing a MLP. It's all very straightforward now because essentially you just stack embeddings to make your feature vector, and then you can use anything you know about until now. You could use tree methods, whatever you want to use. So that's the idea. There's a few PyTorch implementational things that we should talk about because this is now a little bit tricky because you want this to be a learnable matrix, but now you can see it's kind of embedded in a larger matrix and copied. You don't want these to be different E's. So there's a question about like how do you actually do all this in PyTorch? And it turns out PyTorch has some very nice tools to work with embeddings that make this super easy. So we'll talk about those in the next class. So I'll see you guys on Wednesday, and then we'll have the exam on Friday.